that we've been talking about with stat mech is that if you have a group of systems that can occupy different states, the one that you're going to see the most of, the one that's going to dominate, is the one that can be achieved in the most number of ways, which intuitively it sounds reasonable. And then furthermore, we said that if you have a really large system, like say Avogadro's number of molecules, then you're really going to see that dominate even more. So that's a little abstract. So I cooked up this little calculation here. And what the calculation does is we're dealing with a simple two-state system. There's two states, heads and tails. All right, so we're talking about flipping a coin. But instead of just flipping one coin a bunch of times, let's say we have a box of quarters. We shake the box of quarters, and then we take a peek inside, and then we count the number that are heads or tails. And we report the number as a percentage of heads. Right? So you expect 50% heads to dominate, right? So here's our simulation. So right now I have it set up so that there are 4 quarters in the box, and we shake it 4 times. So if we look at the results here, we've got, it looks like once we got no heads at all. So we have a 0% heads, we have a 25% heads. So that happened once. Once we got 1 head, once we got 50-50, and once we got all tails. So we're not seeing what we expect to see, right? Because if you think about the number of ways that you can get these things, there's only one way to get all heads. There's only one way to get all tails, right? There's 4 ways to get 1 quarter on heads and 4 ways to get 1 quarter on tails. But then for 50-50, 2 heads, 2 tails, there's 6 ways to do that. So you should see the most of that. But we're not seeing that. So the problem right now, and by the way, this little program here, it randomly selects between 0 and 1 for each time. This isn't just a graphic. We're actually doing the experiment. With our 4 coin flips, we're not seeing the distribution we expect right now. So we call this, we say this is an undersampled system. But we only shook it up 4 times, right? So let's shake it up a bunch more times. So let's say we got some poor grad student like myself to shake this box 3,000 times and count the number of quarters, right? So if we shake this thing 3,000 times, now we see this distribution. So looking at that, this makes a lot more sense, right? What's the shape? It's Gaussian, right? We're seeing a Gaussian distribution. So now we've sampled it enough. Turns out 3,000 times is enough times to shake this box to the point where we see what we expect to see. And if you look at these peaks relative to each other, we see the most at a 50-50 split, but there's still a good number that you have 1 head and 1 tail on either side of that. Because remember, there's 4 ways to get that and 6 ways to get a 50-50 mix. So it makes sense that they're pretty close, because it doesn't have that much of a lead, 6-4. Not that, that's not going to dominate. And also, we still have a pretty fair showing for all tails and all heads, right? So we ran this experiment 3,000 times. The numbers are kind of small, so I'll read them to you. We have, it looks like about 200 times we ran the experiment, we got all tails, and another 200 times we got all heads. And if you think about that, if you shook a box of 4 quarters and you got all heads, you wouldn't be that freaked out by it, right? You wouldn't go, oh, it's weird. That's not that weird, right? Because there's only 4 quarters in there. So, so let's play with this a little bit. So we'll leave the number of shakes at 3,000 so that we know we're sampling our system well for all of these times. But let's up the number of quarters. So let's say there's 8 quarters in the box. So now I put 8 in there. Now you still see a Gaussian distribution, right? And it looks like we actually still got a few that were all heads and all tails. Because that's a little more weird. 8 quarters all on heads or tails. But we did shake this thing 3,000 times. But if you notice, it does start to tail off by a little after, maybe around 10% heads and 90% heads, right? So you're starting to get, our Gaussian's getting more and more peaked. So that's 8. Let's try 22. So now you're seeing, it's getting more peaked, even more. Now it's tailing off by around 30 and 70%. Let's try 222, just so I can keep hitting this 2 button. It's convenient. OK, now look, 50% heads and tails is really starting to dominate now. So we've got 222 quarters in a box. We're shaking it up 3,000 times. So now we're, have got some real statistical significance here. And now it's tailing off by like about 45 and 55% heads. So now let's try 2,000. Let's see what that does. I'll do it with all 2s. So on the order of 2,000. OK, so now our histogram is starting to get really simple. Now, we're not even sampling below 48 or 52. Like, we're never getting that. And remember, this thing is totally random. Like, it's not, there's no funny math going on. It's just selecting between 0 and 1 a bunch of times. And as you can see, we're not even seeing those less likely configurations. So now, like, the number of ways you can get 50% is on the order of thousands, whereas there's one way to get all heads. So we're not going to see that. And if you think about that, if you shook a box of 2,000 quarters and got all heads, you'd totally freak out. Right? I would. So just to max it out, I set this thing to go up to 3,000. So it goes a little more. So if we're talking about an ensemble of quarters, you can see how like 3,000 sounds like a lot. Like that's a lot of quarters. But if we're talking about molecules, that's like nothing, right? Because Avogadro's number, we'd have to add 20 zeros to that 3,000 to get on the order of a mole. So if it dominates this much for a two-state system with just 3,000 quarters, you can imagine that if you had a whole mole of molecules, how the configuration that has the most number of ways would really start to dominate. So that's why I did this demonstration. Is I tend to be an incredulous person. If you tell me this is going to dominate, I'm like, well, really, it still could happen. But sure enough, if you actually run the calculation, you really don't see those unlikely configurations happen. So hopefully you believe in that sort of thing now. All right, so let's get to the regularly scheduled programming. So if we're talking about, so this leads me into Lagrange multipliers. So the strategy with Lagrange multipliers is we want to maximize the number of ways, right? Because we just proved with our coin flipping experiment that the configuration which shows the highest number of ways to get something is one that's going to dominate. So if you, so that's the function we want to maximize, right? So that the formula for figuring out the number of ways of doing something is right there. It's the one with all the factorials in it. But the thing is, factorials are really difficult to deal with mathematically. So there's a trick. We take the log of it. And the reason we take the log of it, a logarithmic function is something we call monotonically increasing. And you guys have seen the plot of a log function, right? It does that. It doesn't suddenly drop or start going crazy at the end, right? It just keeps steadily increasing. It increases more slowly, but nonetheless, it's always increasing. Therefore, if you take the log of some function w, wherever that log function has the maximum, it's going to be the same as the maximum for our simple equation with the factorials there. So that's why we're allowed to take the log of it, because the max is going to be in the same place for both functions. And the reason we want to take a log, there's one more step, one more little trick. We've talked about Stirling's approximation. And what Stirling's approximation allows us to do is we can get rid of those factorials, because like I said, they're really difficult to deal with mathematically. So that's why we're actually maximizing the log of w and not just w, is because it allows us this trick to get rid of the factorials. And the maximum we find is going to be the same maximum that we would have found had we done it the hard way. So it's a nice little trick to do that. And this is how the partition function gets derived. So we're not looking for a global maximum. We have constraints, right? Like so, with the coin flip, there was no like energetic constraint type thing. But for our molecules, we're imposing two constraints. The one is that the total number of molecules never changes, and the other is that the total energy of the system never changes. So because of that, if we add up the number in each state, we should get the same number every time. I.e., if you have 3 more in one state than you had before, those 3 had to come out of another one, right? We're not just producing molecules out of thin air. In the same way, we don't lose any molecules. And the same thing happens for the energy. If you add up all the energies, if you add the energy of each individual molecule, the total needs to remain the same all the time. So those are our two constraints. So since we're maximizing a function with two constraints, the best way to do it is with the method of Lagrange multipliers. So here's how we do Lagrange multipliers. So the basic trick with this, if you wanted to maximize a simple one-dimensional function, you take the derivative of it and figure out where that function has a zero derivative, right? Because that's where it's either a maximum or a minimum. It's an extremum. So if you have a function of multiple variables, then you're going to do the same approach, but you're going to take a partial derivative with respect to all the variables and add them up, and that should be 0. And that's where your maximum is. But now that would be for a global maximum, but we're interested in a maximum with respect to some constraints. So the way you do that are these three equations at the bottom. They're just for arbitrary variables, x1, 2, and t. The way I prefer to think about it, I like to move the term with the lambda in front of it to the other side and think of it as the derivative of the function is equal to lambda times the derivative of the constraint. And that just resonates more with me, but it's the exact same thing. And the rationale behind this is it has to do, I won't get into it too much because we just want to use it. We don't need to prove that Langrange multipliers works. We'll leave that to the mathematicians. But basically, if you had like a normal vector coming off of both surfaces, the point that satisfies these conditions is when they're parallel to each other. So if the vectors are parallel to each other but not necessarily the same length, the lambda is what you multiply the 1 by, the factor, to make them the same length. So, and then that's where these derivatives are equivalent. So they're equivalent in like kind of their angle, but to make them the same length, that's the multiplier. And that's what links them all together. So the lambda is kind of what ties everything together. And we can actually use it algebraically to help solve these things. So it'll make a lot more sense when I do an example. So first example, let's say we want to make a play area for a puppy. But we only have 40 feet of fence material. So we want to give the puppy the most amount of space to play, right? Because we're nice people. So we want the most area with a set perimeter. So we can only do so much with the perimeter. And another thing is that we've decided we're making this thing rectangular by the way that we've defined the area, right? So the area is just length times width, or x times y. And the perimeter is locked in at 40. But to get the perimeter, you just add the two x sides and the two y sides, and that gives you the perimeter. So we have a function we want to maximize with respect to a constraint. So we apply our method of Lagrange multipliers. So the first thing we want to do is take all of these partial derivatives. So you take the partial derivatives of the function and the partial derivatives of the constraint. And they're nice, easy functions to work with, so we can do all these in our head. And now remember what I said, that the derivative of the function with respect to some variable is equal to lambda times the derivative of the constraint with respect to the same variable. So you're going to have y equals 2 lambda and x equals 2 lambda, right? So good, got that right. So we have our y max and our x max and y max equal 2 lambda. So then we can plug this into the constraint. If you plug that into the constraint, the only variable left is lambda, so we can solve for lambda. So lambda, we figure out, is 5. And now we can plug that back into the 2 lambda, and we see that x equals y equals 10 feet. So the biggest area we can get for the dog with 40 feet of fence material is a 10 by 10 square, which you probably could have, you might have guessed that without doing Lagrange multipliers. But don't overlook this example when you're studying, because it's nice to look at something really simple and just focus on the technique. So yeah, don't dismiss this sort of thing. They could be really useful study tools. So yeah, 10 by 10 square. All right, now we're going to do one a little more complicated. So now we have something called a paraboloid, and that's that yellow surface. I tried to make it UCI colors. It looks a little greenish, though. But so the paraboloid is that dome-looking thing. And then we have a constraint of this, the plane, the blue plane. So the idea, we want to find the highest point on this function, so that f of xy is the yellow function, and the constraint, the y minus x, is the blue plane. So if we wanted just the global maximum of that paraboloid, we'd just walk to the top of the mountain and we're there, right? But the problem at hand is that we have to walk in such a way that we're touching both the plane and the paraboloid, and then find the highest point, right? So it looks like it's somewhere off to the left, right? But so just kind of looking at it, we know it's going to be somewhere around there. But let's do the math. So the first thing we want to do is take the two derivatives of the function. And so we have those there. We use the chain rule. That's how you get the 2 out front, if you forgot the chain rule. And then if you solve that for x and y, well, then now we have the global maximum, right? So the top of the mountain is at the 0.36. But that's not what we want, right? We want the top of the mountain with the assumption that we have to be touching the plane as well. So that means we need to take the derivatives of the constraints as well. So when we take the derivatives of the constraints, it's just -1 and 1. So then remember, it's going to be the derivative of the function equals lambda times the derivative of the constraint. So we set that up. And as you can see from this, they're both now expressed in terms of lambda. So since they're both in terms of lambda, we can take the one on the left, multiply it by -1, and then they're both equal to lambda. And then if they're equal to lambda, they're equal to each other, right? So we can eliminate lambda and express it this way. So now looking at that, we could rearrange that and say that x plus y equals 9, right? So we know x plus y has to equal 9. And that gets us almost the whole way there. But then if we look back at our constraint, we realize that y minus x equals 0, or y equals x. So if y equals x and y plus x equals 9, then they both have to be 4.5. Everyone good so far? I feel like I'm going fast. Yeah?
For the constraint, how do you know the constraint?
It's given, yeah. Yeah. All right, good. So what's next? All right. So, so those two examples were both the method of Lagrange multipliers, given that you have one function to maximize with one constraint. But for our partition function, remember we have two constraints. You have the total number has to remain the same, the total energy has to remain the same. So you can do the method of Lagrange multipliers with as many constraints as you want, but the more you add, the harder it gets to do. And it doesn't really lend itself well to lecture, because it's one of those derivations that takes so long by the end you forget what you're doing in the beginning, kind of a thing. But it works well for reading, and there's actually a really good one at the end of your chapter in like the further information section for the chapter on the Boltzmann distribution. So check that out. It's a good read. I like it. I don't know. So, but this is the process you would do. We're not going to actually do it, but this is what the process, and it's in the book, where we have all these constraints, and you see that. You subtract them. Well, you know, I like to put it on the other side of the equal sign, but we are subtracting them, right? But in this case, you just subtract the two constraints, and each one has its own Lagrange multiplier. So we have a lambda and a beta. And that beta constant actually does end up being the beta constant that you're familiar with, right? The 1 over kt. So that's all we'll say about actually deriving the partition function. But I wanted you to understand kind of where it comes from, so that you know that e to the minus beta times the energy. It all comes out of this. So it's oh yeah. Is what? F is the largest normal vector. Oh, in the bottom left? F is the function. The extremes. I'm sorry, I'm not really following it. We'll talk after. But yeah, I mean, don't think too hard about the thing I was saying about the parallel vectors, because we're mostly interested in applying this thing. But I just kind of looked it up myself because I was curious and read a little bit about it, and that's what it boils down to. But keep the focus on applying it, especially for this class. But I'm glad you're curious about it. You should definitely look it up. But I can't talk about it now. So we've got. So here's an example of the plots of a few partition functions. So if we're interested in knowing the average speed of an atom of these particular noble gases, if you plotted them, they would look like this. And if you notice that the helium one is a lot faster than everyone else, right? And if you notice the correlation here is the lighter it is, the faster it's going, right? And the reason for this is that temperature is tied to the kinetic energy of these gas molecules flying around in 3 dimensions, right? So if the kinetic energy is what relates to temperature, but kinetic energy has two pieces. It's mass, 1/2 mv squared, right? So there's mass and velocity both tie into it. So basically, if these 4 gases are all the same temperature, then they're all about the same kinetic energy. So if they're all about the same kinetic energy and one has less mass, then it's going to go faster, right? Because it's 1/2 mv squared. So that's why you see this, just kind of qualitatively. So let's talk about finding the average kinetic energy of a gas molecule. So there's our equation for kinetic energy, in case you forgot it. But down here, we have a distribution here. And this distribution represents the probability of finding a molecule in a particular energetic state. So it's a population, right? So basically, you have the state you're interested in over all of the possible states. And so it's kind of like taking a fraction, right? It doesn't look immediately like a fraction because you have an integral on the bottom, right? But if you remember, an integral is a way of approximating a summation, right? So if you have a summation and you're adding all these things together, an integral is a way of approximating that, right? And you can think of, if you have the area under the curve and you divide it all up into a bunch of little boxes and you find the area of each box and add them up, that's the summation, right? So the function will give you the height of the box. So you have the function times the change in the x-coordinate, which is your dx, right? So it's right there when you take an integral. You're really just taking a bunch of areas and adding them together. So that's why it doesn't immediately look like we have the sum of a bunch of different possibilities on the bottom and one possibility on the top. But that's what this is. But we can simplify it a little further. So that function on the bottom there is just the integral of a Gaussian, which is a very well-known integral. So there's the rule. If you see the a there, that's your constant. So in this case, our constant is just 1/2 beta m, right? So then that's how we go from the equation on the left to the one on the right, is that we just perform that integration, and it's a constant. So then that goes out front. So now this is going to represent our population in a more concise way. All right, now let's say, so we're interested in the average kinetic energy. So you'd think, all right, we need the average velocity to get that, right? Because we know the mass, it's going to be a constant of whatever we're dealing with. But we need the average velocity to figure out what our average kinetic energy is. But if you take the average velocity, say in one dimension, so when we're just in the x direction, you've got an equal probability of going right and left, right? So whatever distributions of speeds you have going right, you're going to have that same distribution going left. So the average of all of them is just going to work out to 0. So we can't do that. So instead, we're going to take, instead of the average velocity, we'll get the average of the square of the velocity, which is called the variance. And you guys should be familiar with variance. And if you're not, you're definitely familiar with the square root of the variance, which is standard deviation, right? I think people like to ask about after there's a test, right? So we're looking for the expectation value of the velocity squared. Now, what's important to notice about this integral here is you've seen this type of treatment before when you took quantum mechanics, right? Because quantum mechanics, your wave function, when you multiply it by its complex conjugate, gives you a probability distribution, right? That's what a wave function is when you multiply by its complex conjugate, it gives you the probability distribution of where the particle could be, right? So if we're interested in the average position, we took our position operator, which in one dimension is just x, and you sandwich that in between the wave function and its complex conjugate, right? So you're essentially multiplying the thing we're interested in by the probability density. And we're doing the exact same thing here. It's just that we start with a probability density, so we don't need to multiply anything by its complex conjugate. But it's the exact same process. And then you integrate it over all space that you're interested in. So that's what we're doing. And it's essentially a weighted average, right? So when you add, so going back to how an integral is really the limit of a sum, it's kind of the same thing in that this variable, we multiply it by whatever that function is at that point, and then you keep adding them together. So what you have is a weighted average. And we'll do an example later where we don't need an integral because there's a small enough amount of states that we can actually just take a standard weighted average. So keep that in mind. OK, so that's why we set up the integral the way we do. So now let's take the integral. So if you notice, v squared is an even function, and a Gaussian is an even function. So you have even times even is even. So trick with even functions is you don't need to integrate the entire thing, right? You can integrate only to the right of 0 and then just double it, right? Because whatever area is on the right side is the same as on the left. Property of even functions. And also, while we're talking about that, let's think about, remember how I said with the velocity, just qualitatively, we can't get an average velocity because it can go right or left. If we look at this thing mathematically, if we just put a v there instead of v squared, v is an odd function. So you got odd times even. So if you take that integral, you get 0. So the math works out as well. It matches our intuition in that your average velocity is going to be 0. Which is one reason why things like variances, standard deviations are so important, because sometimes you can get more information from that than you can from an average. Average is just kind of the go-to thing because it's easier to understand. So if we solve this integral, it's also a well-known integral. It simplifies down to 1 over beta m. So the average velocity only depends on 1 over beta m. So we were out to get the average kinetic energy, right? So that's 1/2 mv squared. And if we have the average value of v squared, we could just plug that right in. So the average of the square of velocity is, the average kinetic energy works out to be 1/2 kT. Right? So it's nice, simple, just works out to 1/2 kT. But since not too many experiments are run in an infinitely long tube of infinitely small diameter, right? Because that's what we'd have if we had molecules going in one dimension. We need to worry about the other 2 dimensions, right? But this is an ideal gas. So we can work on the assumption that the velocity in the x, y, and z are not correlated with each other in any way. So if that's true, then we can treat it as a linear system, meaning we just add them up. So if you're interested in your average kinetic energy in all 3 dimensions, you just add it up for x, y, and z. So instead of 1/2 kT, it's just 3/2 kT. We just multiply it by 3 to account for all 3 dimensions. All right? So that's how you figure out the average velocity of an ideal gas molecule. OK, and so as we showed, the average velocity or the average speed is due to the hotter it gets, right? So this is just this just shows a few Boltzmann distributions for different temperatures, and you see that as it gets hotter, 2,000 degrees Celsius, the average is, the center of that distribution is much further to the right, and it's more spread out. And it spreads like that because more states are energetically accessible, right? All right, so now we'll do another example. This is a cool one. So for this one, let's say we're exposing some paramagnetic substance to a magnetic field, right? So you have all these magnetic dipoles that can point in any way, right? And when you put a magnetic field on it, they try to align with the magnetic field. So then there's a statement, heating a magnet makes it lose its magnetization and why. So if we think about the situation of like a permanent magnet, like something on your refrigerator, that's probably ferromagnetic, but we'll go with it anyway. If you've got a field that's trying to align all the dipoles in the one direction, then heat is just kind of somebody walking around just kicking them all over the place. So the idea is heat. So Richard Feynman, one of my favorite scientists in history, used to talk about how atoms jiggle, right? So if you have any substance, the molecules, the atoms are all jiggling around. And the hotter it gets, the more they're jiggling. So the same thing happens in a substance that has magnetic dipoles. But the dipoles get kicked around as the atoms get kicked around. So the hotter it is, the more you're kicking these things around randomly. So you've got 2 competing things. You've got a magnetic field that's trying to align the dipoles in one way. And then you've got heat just kicking it around randomly. So that's why you can make a magnet lose its magnetization by heating it up. Because so with like a permanent magnet on the fridge, what it is you expose it to a field long enough, and they all kind of just get stuck that way. But if you heat it up, then you're kind of giving them energy to jiggle around all over the place, and then they're randomly aligned. Yeah?
Is that why when you cool a magnet, it gets stronger? Or
That's a good question. I don't know about this effect.
the dipoles even more? Or
To be honest, I don't know. I'm not going to try and fake an answer because I'm not sure. I'd have to look that up. But I know, with superconductors that you can have like, electromagnet often have to run really cool. But I don't know about just cooling a permanent magnet and if that increases the field. I've never heard of this, but that doesn't mean that it doesn't exist. So we're going to approximate the system as a what do you call it? A two-state system, right? So we've got all these dipoles. They can point any which way, but we'll just say, and it's a good approximation, we'll just say that all of these dipoles are either pointed with the field or against the field, right? So then if it's with the field, we'll call it parallel. If it's against the field, we'll call it antiparallel. So which one do you think is higher energy, antiparallel or parallel? Good, antiparallel, because you want to think about potential energy, right? So if you have potential energy, it's pushing on it, it wants to pop over, right? But once it's popped over, it's not going to do anything else, right? So it's like dropping something, potential energy, right? If you already fell on the floor, you can't fall any further. So same kind of thing. So let's see here. So the energy for the ground state, we're going to call that negative mu naught B naught. And then if it's antiparallel, then it's going to be the same unit, but positive. So therefore, the energy difference is going to be 2 mu naught B naught. So if we want to, so there's our energy difference. So let's try and find the partition function. And remember, so the partition function was in that previous example, that one on the bottom where we had that integral of all the possibilities. But for this particular system, there's only 2 possibilities. So we don't need an integral to do it, right? All we need is a weighted sum of these different states. And these states that we add up, and if you take one thing out of lecture today, don't forget this. It's going to be the degeneracy of that state times e to the minus beta times the energy. So that's how we got the 1 and the e to the minus 2 beta mu naught B naught, is because, so the ground state we always call 0. Because we can establish our energy scale any way we'd like. And then later, if you need to correct it for 0-point energy, you can always add it back in. So you always call the ground state 0 energy. So we have 0 energy. And the degeneracy of both of these states, there's only one of each state, right? So the degeneracy is just 1 for both of these. So you're going to have e to the 0 is our ground state. So that's why we have 1. And then you're going to have e to the minus, or e to the minus beta times 0. So e to the 0. And then you're going to have 1 times e to the minus beta times the energy, the amount of energy we've raised, which is 2 mu naught B naught. So this is our partition function, Q. Now, from the partition function, we can figure out the population of each state. So remember how I said it's a fraction, right? You have so many, you have the one particular state you're interested in over all the possible states. So that's what we have. So for the ground state, the first term, it was just 1. So you have 1 over Q gives you the population in the ground state. And if you're interested in the population in that the excited state, that's going to be the second term. So e to the minus 2 beta mu naught B naught. And then you divide that by your partition function. So those are our populations. So now if we're interested in the average magnetic moment, the way we're going to do that, it's going to be a weighted average again. So the weighted average is going to be the magnetic moment times its population in that particular state. And so this is our weighted average. If you had me in discussion, you've seen this with, if you have a certain number of people in the room, all of different ages, and you want the average age, you'd add up the number of people, or say like 5 12-year-olds, and 20 20-year-olds, right? You'd have 5 times the 12, and then you add that to the however many 20-year-olds times the 20, and then you divide that by the total number of people. That's a weighted average. It's the same thing here. So if we've got that now, so for the first one, for the magnetic moment of pointing with it, so that's positive mu naught, you just multiply it by the population that's in that state, which would be the P naught up there. And then the state pointing against it, we're calling that negative mu naught. Then you multiply that by the population in that state, so that's the P1. And then all the way to the right, we've just expanded that. So if we want to get fancy, we can realize that this is the definition of the hyperbolic tangent, and you can write it that way. But that's not as productive. Instead, we're gonna make an approximation here. And approximations are OK, but they have to be justifiable, right? So the way we're going to justify this is, let's say that we have a weak magnetic field or a high temperature, right? So remember, we have these dominating forces. We have the magnetic field that's trying to get everyone to line up evenly. And then you've got the heat that's just kicking everything all over the place randomly. So we're saying that the heat is winning, basically, right? So, and you can do that with just a really weak magnetic field, or you can do it with really high heat, right? You can do it either way. So the important thing is that the ratio is much less than 1. So if this is much less than 1, then the strategy we're going to use is doing a Taylor series centered at 0. So if you remember with Taylor series, the idea is your Taylor series is always centered somewhere, right? And wherever it's centered, the closer you stay to that point, the more accurate your Taylor series is, right? And if your Taylor series, and if you're staying really close to that point, then your Taylor series approximation can be pretty good with just a few terms. So that's kind of the approach that we're taking here, is that we can expand this to a Taylor series and only use a few of the terms because we're so close to 0 and we're centered at 0. So technically that's a Maclaurin series, right, if we're centered at 0. So looking at this first expression in the parentheses, and remember this came from the numerator of that fraction, right? This fraction in the bottom left here times the mu naught. That's what we're working with, but we're finding an approximation for it. So the Taylor series for e to the x is just 1 plus x squared over 2 plus x cubed over 6, right? So it follows that pattern. But we're just going to take the first 2 terms and call it good enough, right? Because we're really close to 0. So the way we're going to do that, so the first 2 terms of this, imagine we take that exponential function right there. It would just be 1 minus, so we'll call that entire thing, that 2, the minus 2 beta mu naught b naught, that entire thing we're calling x. So then the first 2 terms will be 1 plus x, or in our case, 1 minus 2 beta mu naught b naught. So those are our first 2 terms of the series, and we're going to stop at 2 terms. So now if you distribute that minus sign in there, then you get 1 minus 1, so the 1's go away, and you're just left with 2 beta mu naught b naught. All right? So that's the approximation for the numerator. Now if we look at the denominator, we'll do the same thing. Take the first 2 terms. So you're going to have 1 minus 2 beta mu naught b naught. But this time the 1's positive, so you get 1 plus 1 equals 2. And then you subtract the 2 beta mu naught b naught. So now we can make even one more approximation, because up top we said that our beta times mu naught b naught, remember beta is just 1 over kt, is really small. It's much, much less than 1. So if that's true, then we're subtracting a really tiny number from 2. We don't really care if it's 1.99999 something, or if it's 2, right? We're just going to say it's 2, because it's so close to 2. So we're going to approximate the denominator as just being 2. And then if you write that out with this fraction, this is what you get. So the expectation value for the magnetic moment for this particular substance in a weak field at high temperature is just mu naught squared b naught over kt, or times beta, however you want to say it. So this is known as Curie's law. Whoa. This is known as Curie's law, and here's a plot of it. And at high temperature, populations tend to equalize. And this kind of confirms what we were thinking about just kind of qualitatively, right? If temperature is just kicking these dipoles all over the place, and our magnetic field is too weak to try and keep them aligned, you're not going to see much of a net magnetic moment, right? So that's what we have here. Any questions on that? OK. We're just blowing through this stuff. Am I going too fast? Am I? Is there anything you want me to back up to? No? Well, if we get to the end and we have time left, let me know if there's something you want to rehash, and I'll do it. From the Northeast, too, we tend to talk fast, so I don't know. All right, so now we're doing an example that's kind of near and dear to my heart, a protein folding example, right? So we talk about, we talked about like toy problems, right? So like in quantum mechanics, a toy problem would be like a particle in a box or a harmonic oscillator, right? So now for protein folding, right? So when proteins are synthesized in the body on the ribosome, as they come off the ribosome, they fold in all sorts of different ways because the different amino acids are attracted to each other in different ways. And so they kind of fold up into this shape and do so really consistently. And that's what gives them their function, is their structure. So it's a really fascinating area of research. So you can kind of look at this as a toy problem for protein folding. So we've got 6 beads, like a string of 6 beads. And we're going to say that these beads are all attracted to each other. So we'll say kind of like van der Waals forces. So these beads are all attracted to each other. And they can bend around in different ways and possibly stick to each other. So we're going to look for a partition function for this thing and figure out the populations of these different states. So as an approximation, let's say that these things can only snap into place at right angles, right? So if the only bending this thing can do is at right angles, there's 21 different ways you can configure this. And you can thank Dr. Martin for drawing every single one of those things. That must have taken forever. So you have all these states here. So there's 21 different ways you can bend this thing at right angles without having anything touch. If you allow 2 of these beads to touch, there's 11 ways to do it. And if you allow 2 contacts to happen, there's 4 ways to do it. All right? So these are our microstates. So when I say like there's 4 ways to do it, 11 ways to do it, 21 ways to do it, what am I talking about? This starts with a D. Degeneracy. Good, good, good. So we're talking about the degeneracy of these different states. Because energetically, we're going to say they're the same. Right? They're the same state energetically. We're only showing 3 different energetic states. But the first one, they all have different degeneracies. There's more than one way to do it. So now let's try and figure out which one do you think is the highest energy state? What do you think is the lowest energy state? How about the bottom, the one with the 4 microstates? Do you think that's the highest or lowest energy? Lowest. Good. And again, we're thinking of potential energy thing here. So if these things are attracted to each other and then they collapse together, if we look at the one with the 4 microstates, it's already collapsed, right? It can't collapse any further than that. So that's going to be our bottom one. That's going to be like our ground state. And then, so then one contact would be the first excited state, I guess you could call it. And then the highest energy state is the one with the 21 microstates there. Is everyone good with that? So let's try and find a partition function for this thing. OK, so first of all, this is the energy we were talking about, right? Energetically, they're all the same state. There's only 3 different energetic states, but they have the degeneracy. And we're looking at it, again, kind of a linear relationship between energy and number of contacts. So the less contacts there are, the higher energy you are. So that's why we just kind of went linear relationship here. If you look at the coefficient in front of E naught, it goes 0, 1, 2, right? So here's our partition function. So looking at the ground state, there's 4 different ways to make that ground state. So our degeneracy is 4. And remember, we always call the bottom energy level 0. So then you have e to 0, which is 1. So our first term is just 4, right? Because degeneracy 4 times e to the 0 is 1, 4. Second one, there's 11 ways to do it. And our function is, the energy for that particular state is E naught. So it's e to the minus E naught times beta. And then the last one, there's 21 ways to do it. And the energy we determined was 2 E naught. So that one's going to be 21 times e to the minus 2 E naught times beta. All right? So remember this for writing these partition functions of these smaller systems that we can actually write out every term of the partition function. So typically things are too complicated for this to get them all, but we can have these toy problems like we do in quantum mechanics to look at that. And you can have a partition function of, so like the one with that we determine the average kinetic energy of the gas molecules, we're talking about translational energy, right? Which is a really good way to describe the energy of those atomic gases, right? Because the atoms are considered points as far as the mechanics of it go, for the most part. So all you're interested in is translational energy. But you could have a gas that's like big and it can rotate, right? So then you'd have rotational partition functions as well. So there's all kinds of these partition functions you can come up with.
A question.
Yeah?
How come you write beta as 1 over kt here?
It's equivalent. So beta equals 1 over kt. I prefer to always use beta. Dr. Martin was saying this, that experimentalists tend to favor 1 over kt because temperature is something you can actually, temperature is the more natural unit if you're running experiments. And theory people tend to favor beta, so maybe that's why I favor beta. I don't know. So yeah, and I think I just out of habit called it beta every time, but it's equivalent. Any other questions? We have almost a little over 5 minutes if there's anything you'd like me to do again. If not, we can call it a day. It's up to you. No? All right. Well, thanks. Thanks, guys.